Two carts and a spring. Two carts and a spring. Cart A, with a mass of 0.35 kilograms, moves along a horizontal frictionless track with a speed of 4.5 meters per second, then hits and sticks to cart B, which has a mass of 1.6 kilograms. Initially at rest, cart B is connected to the end of a massless spring with a spring constant of K, 75 newtons per meter, that is affixed to a wall. So it's just sitting there resting up against it. Calculate the momentum of cart A before the collision. What is the kinetic energy of cart A before the collision? Then find the initial speed of the two-cart system, when A is pressed up against it like this, right after the collision and before it starts compressing the spring. Determine the kinetic energy of the two-cart system right after the collision. Is kinetic energy conserved during the collision? Explain. What is then the maximum displacement of the spring after the collision? Calculate the momentum of cart A before the collision. This is frictionless here, so the speed that it starts with is the speed that it strikes cart B with. So the momentum is ma times v0a. The mass is 0.35 kilograms. Here's the initial speed, 4.5 meters per second. And we get a momentum of 1.58 kilogram meters per second. What is the kinetic energy of cart A before the collision? Well, we have our kinetic energy equation, 1/2 m, in this case mass A, times v0a squared. We have 1/2 times 0.35 kilograms. The initial velocity is 4.5 meters per second. Make sure you square it, don't forget that term. And you get a kinetic energy of 3.54 joules. Find the initial speed of the two-cart system right after the collision. So we have cart A striking and sticking to cart B. It's initially at rest. We have a perfect inelastic collision. Why? Because it says it sticks to it. Initial speed of the two-cart system right after the collision means that the spring has not yet started acting on the blocks. So use the equation for the perfect inelastic collision as momentum is conserved. There are no other external forces. So here's our perfect inelastic collision. Initial momentum is final momentum. The initial momentum will be the individual momenta of both carts, A and B. And the final momentum, since it's stuck together, it works as one object. So the combined mass of MA plus MB times VAB. And this is what we're looking for. Cart B is at rest. Cart B is at rest, so we lose this term. We then switch sides here. So we have VAB on the left side, that's what we're solving for. We divide through by MA plus MB, and here's our equation. So please work all of that before you actually plug numbers in, right? Most teachers, if you get that far and let's say it's worth 10 points and you get the wrong answer, you'd probably get 9 points. At least that's what I would do. Then put the numbers in, and then do the math, and you get 0.808 meters per second. Determine the kinetic energy of the two-cart system right after the collision. Use the speed of the blocks that was found in part C in the kinetic energy equation right here. Make sure you add both masses together because they're moving as a system. Here's our velocity, and make sure you square it. And we substitute in our numbers, and we get the kinetic energy is 0.637 joules. Is kinetic energy conserved during the collision? Explain. Well, no. I mean, it's a perfect inelastic collision. That means KE is not conserved, but let's look at the numbers we got. Here is our kinetic energy before. Here's our kinetic energy after. Clearly, a lot of kinetic energy was transformed into other forms of energy. And it was transformed into sound, maybe some deformation of the carts as they hit each other, and heat. What is the maximum displacement of the spring after the collision? So what happens is A hits B, and then they push in on the spring. There are no external forces acting on the system, so we can absolutely use the conservation of energy. We're assuming a massless perfect spring. The carts and the spring are on the same level surface, so we don't need to worry about GPE. It's the same before and after. And at maximum displacement, what does that mean? That means that the carts come to rest, so the only energy is elastic potential energy. Now we go to conservation of energy. E initial is E final. All we have is kinetic energy in the beginning, and all we have is elastic potential energy at the end. We put in our kinetic energy formula, being sure to include both masses, right, because they're stuck together, equals 1/2 kx squared. X is what we're trying to find. That's the maximum displacement. So we switch sides, multiply both sides by 2, divide through by k, and then take the square root over here. And since we have v squared ab inside the square root, we're going to take it outside, right? Square root of v squared is just v. So that'll save us a calculation. We won't have to square it and then wind up taking the square root anyway. So here's our algebraic expression, which again, that's what you solve first before you put any other numbers into the problem. So here's our algebraic equation for the answer. Substitute in our variables, and this is what we found earlier. Velocity of the two blocks right before they started pushing it on the string, and we get a displacement of 0.130 meters. And just reminding you again here, take the VAB squared out of the square root. Makes it a more elegant solution anyway.